All right, let's work on this problem. So given two non-negative integers, low and high, we want to return the number of odd numbers between low and high inclusive. So just working through like a few examples here. If low is 3 and high is 7, 3, 4, let me write somewhat legibly, 6, 7. Odd numbers, we've got 3, 5, and 7, so that will return 3. We've got 8 and 10, 8, 9, 10. We've got 1. Okay, so what we can do here is we can work through a few more examples if we want. But after working through a few examples, we might start to see some patterns that can be useful. And basically, if we have let's say we have A1, A2, A3, A4, A n minus 1, A. Okay, so let's say n is even. Then what we can do is we can break these into pairs. We have A1, A2, A3, A4, blah, 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 AN minus 1, AN. It's always going to break up by like this because if n is, wait. Yes, n here is the number of, integers in this range. So that's why like, yeah, so we have integer 1, integer 2, integer 3, integer 4, blah, blah, blah. So if the number of integers is even, then the number of integers is going to be exactly divisible by 2. So then we can break it up into pairs. And for each pair, it's either going to be even, odd, blah, 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 all the way up to even, odd, or it's going to be odd, even, all the way up to odd, even. And regardless of which case it is, we're going to get precisely one even number in each of these pairs. And so the number of even numbers, no, the number of odd numbers is going to be n divided by 2 because we've broken it up into precisely n divided by 2 pairs, and each of those pairs is going to have precisely one entry. Okay, but what if n is odd? If n is odd, then we have A1, A2, A3, A4, AN minus 2, AN minus 1, AN. If n is odd, then the sequence going from A1 to AN minus 1, that's going to have an, so if this sequence of n integers is, if there are an odd number of integers in this sequence, then if we remove that final integer, then there would be an even number. And so then we can do that same thing that we did before, where we just break things up into pairs all the way up to that final. I'm just going to sort of like wall it off here to show that it's separate. So everything before the final index, actually, to make this easier, it doesn't matter how you do it, but to make it easier, I'm going to wall it off like this. We're going to wall off the first element, and then the remaining elements, there's going to be an even number of them. And so there will be precisely, so how many elements are there here? Going from A2 all the way up to AN? Well, there's n minus 1. And so here, since n is odd, n minus 1 is going to be even. So then n minus 1 divided by 2, that's going to be the number of odd numbers. The n minus 1 divided by 2, that's going to be the number of odd integers in this sequence, excluding the first integer. Okay. But then what you do is you also have to account for that first integer. And the final number of odd integers is going to be, basically we're going to need to add 1 if the integer a1 is odd, or if the integer a1 is 0, or no, not 0, but even. If integer a1 is even, then we just stick with this formula here. Otherwise, we have to add 1 because a1 is odd. Okay. So we return this plus 1 if a1 is odd. Okay. So that's basically the formula. And just to show this in a little more detail, let's say we had like, because if there's an odd number of integers, it would either be even, odd, blah, blah, blah. So let's just go with 5. Even, odd, even, or odd, even, odd. So going through this process, we have this, and this, and this, and this get grouped together. And so we take, after we remove the first integer, there are 4 integers remaining. And we break that into pairs, and so we get 4 divided by 2, which is 2 odd numbers. Then, whether or not we add 1 depends on whether that first integer was odd. So this will give us 2, and this will give us 3. Okay. So, and again, this is n equals 5 here. So this is 5 minus 1 over 2. This is 5 minus 1 over 2 plus 1. There. Okay, so that's the exact formula. So let's actually type this out. So we're going to let n be, let's see here, n integers. Well, let's just say n. N is going to be the number of integers. And so it's going to be, okay, now this is tricky. So how many integers are there? So let's take this example, 3 to 7. So 3, 4, 5, 6, 7. There's 5 of these. 7 minus 3 is 4. So because this is inclusive, we need to take high minus low plus 1. And that's going to be the number of integers in this sequence. And this is really sort of interesting if you think about it, because this almost feels like an off by 1 counting issue that you need to account for. But this has nothing to do with Python being a language that starts indexing at 0. I think this example sort of shows that like these off by one counting issues, these aren't issues that are like specific to computer science and programming. I think these are really like inherent issues about counting in general, and also sort of the way that we translate from language into mathematics, because here the count of odd numbers between low and high inclusive, adding in the inclusivity is what causes this, or specifying the inclusivity is what causes the off by 1 error. Maybe that's sort of a tautological, either a tautological or a non-meaningful statement to talk about like the English semantics interacting with math and stuff, because but in any case, counting is hard, and counting is hard even if you are not a programmer. But yeah, okay, so n is the number of integers. And so again, let's go back to this. If n is even, then we just return n over 2. If n is odd, we have to check that first entry and add 1 depending on whether that entry is odd or even. So if n is even, meaning that n mod 2 is 0, then we are going to return n divided by 2. This is not going to work because in Python, division returns floats. And we need to return an integer. So we're going to do this floor division, which takes the integer, this is like the floor, this is like you divide and then you take floor. So it's the largest, so a/b is the largest integer that is less than or equal to a divided by b. And I guess like I don't fully understand how like floating point numbers work, and so I was sort of like concerned, like, okay, is there some like weird scenario where even if like because in this scenario n is an even number, so n divided by 2 like mathematically gives you an integer. But is there some weird like programming rounding thing where like there could be some cases where like n is an integer, n is an even integer, but somehow dividing by 2 gives you like, I don't know, like let's say if n is 4, could it be possible that 4//2 would give you like 1.9 repeating, and then this formula would give you 1 instead of 2? And I looked it up, and according to the internet, Python does not do this. According to the internet, if a is divisible by, if a and b are integers and a is truly divisible by b, then a//b will give you the precise answer. And so we don't need to worry about any like erroneous rounding errors when we do this division with 2 slashes. This is just to enforce that the output is an integer. Maybe we could have just done like int n over 2. Let's try it, because I know that this code will work with n//2. Let's just try this and see if it works. Okay, so if n is even, we do this. Otherwise, we have to check if the first element is odd or even. So if the first element is, and there's no reason that we could, for this, we could check either the first element or the last element. It doesn't matter, but I'm just going to choose the first. If the first element is even, then we are going to return, okay. Then we are going to return n minus 1 over 2. So this is going to be int of n minus 1 over 2. Otherwise, we're in the scenario where n is odd and the lowest integer is odd, and so we're going to return 1 plus int n minus 1 over 2. Okay, and now we can submit this. No. Okay, and there we go. Interesting. So this is a little bit slower. I think if we, I think it went faster when we used, when I used floor division. Guess not. Well, I tried. Okay. But yeah, so this is basically the answer. The only other thing that I thought about is, well, no, because you always have to do the n minus 2. Yeah, so basically you just need to sort of, yeah, I think there are some ways to improve this. Wait a minute. If this is floor division, do we even need to subtract 1? Because won't it just give you like 0.5 and then round it down? Yeah. Wait, why did that go slower? I feel like that would have gone faster. But yeah, this is interesting. The only other thing I thought of is that, like, you know, if you wanted to make the code as concise as, maybe it's doing this is slowing it down. But whatever, it doesn't matter. The only other thing I thought of is that, like, now with the way that this code, by the way, I should probably talk through. So the reason that this is the same as n+1/2 or n-1/2 is that, like, because n is odd, okay, basically, I'll just leave this. If n is odd, n/2 is equal to n-1/2. Why can we prove this real quickly? Hold on, I'm on a roll here. How would we prove this? So n/2 is equal to n-1/2 plus 1/2. So the floor of n/2 is going to be n-1/2. So, and remember, the floor of n/2, that is precisely by definition n/2. And here on the right-hand side, n-1/2 is equivalent to n-1/2 because slash and slash are the same when the numerator is even. And the numerator is even in this case because n is odd, so n-1 is even. Okay, cool. That was a nice little quick proof. Okay, so now looking back here, if we want to make the code even more precise, we really only need to check for one scenario. Basically, it's going to be n/2 except for this one other scenario. So if n is odd and low is, so n has to be odd and low has to be odd, then we return n divided by 2. No, then we return 1 plus n divided by 2. Otherwise, we return n divided by 2. I do wonder if this will be slower because, like, this sort of can break us out of the code more quickly. And so maybe here, like, because we're just checking for a very specific scenario and we check for it every time, maybe that will slow it down. But let's try this. Oh, well, that did better. Okay, so yeah, nice. So yeah, there we go.